We've already done a session on winds, you'll remember. And just to remind you, the cause of wind is essentially starts off with the temperature differentials from the equator to poles caused by the uneven heating of the Earth's surface by the sun. Then also we have rising and sinking air then leading to pressure differentials at various points. And then, of course, air moves from high to low pressure to equalize the differences. So it's all these temperature and pressure differentials in the pot of fluid that are moving around all the time to try and equalize and find an equilibrium. Of course, that's complicated by the Coriolis force, the apparent force caused by the Earth's rotation, which has an effect on wind and particularly the direction of the wind. And that's like a rotating, I suppose, never-ending sequence. You'll remember we discussed global circulation, and in doing so, we looked at the three cells where there would only be one cell if the Earth weren't rotating. But of course, because of the rotation of the Earth, it's more complicated. And also because of the different land masses. Predominantly, the land masses are in the northern hemisphere rather than in the southern hemisphere, where you have much more ocean. So that has also got an impact. We've got the high and low pressure zones that tend to be semi-permanent. You can see the high pressures there, either side of the equator, and then, you know, the low pressures are very often at around our latitude, and also in the similar latitude to the south, in the southern hemisphere. And of course, these then lead to what would be the prevailing winds, the trade winds, as they were called in the days of sailing ships carrying their cargoes east and west across the oceans. So these are semi-permanent global winds caused by global circulation. Of course, they also lead to very distinctive climatic zones, where we've got the rainforests in the equatorial areas, and then either side of the equator we tend to have the desert areas, and then north of the desert areas then we have the temperate areas that would be associated with our climate. So all part of the global circulation system and global winds. But tonight we're just going to look at some specifics that lead to local winds. And what are they? They're also, you'll see them referred to as mesoscale, just means small scale winds. They're also called regional winds. So you can find those three terms: mesoscale, small scale, regional winds, depending on what source you're reading. They're largely driven by temperature, localized temperature and pressure differences, especially between land and sea, and we'll see some of that later when we look at sea and land breezes. Also variations in topography, height and shape of the Earth's surface have very distinctive effects on local winds. Local winds are winds that range from just a few kilometers to about 160 kilometers in width, according to the definition, and also they can persist anywhere from several minutes to several days. Talking about some well-known examples, this is one that's quite common in northern Africa, the Mediterranean. You might have even read in the papers or seen in the news not so long ago about very red dust affecting southern Europe. I didn't get a chance to look specifically at the cause of that, but I would suspect it was something like we're looking at here, the Sirocco wind. It's a well-known local wind. And it's caused, as you can see there, by low pressure in the Mediterranean moving eastwards. And it kind of, you can see it, the rotating air mass bringing the hot, dry tropical air from the Sahara over the Mediterranean, and it can tend to lead to storms in the Mediterranean and cool, wet weather in Europe. Here's another one that's quite well known. It's called the Cape Doctor. That's Cape Town. And in the distance, Robben Island. So the Cape Doctor is a strong, dry southeasterly wind. It blows over the South African coast from spring to late summer. It's called the Cape Doctor because it's believed that it clears Cape Town of pollution and in the old days, pestilence. And it just reminds me that local winds are very, very important because many of them occur in this border between land and sea. And of course, a lot of cities and lots of the population are based at that border as well. So they're very, very significant, not just in aviation, but also for populations close to the sea. Another one you might have heard of is the Chinook winds, or Chinook, depending on what part of the US you're in. Northwestern America, not just US, but Canada as well. There's two types. One is a wet southwesterly wind blowing in from the ocean, and the other is actually a foehn wind. And we'll come to foehn winds later on in this presentation. These blow down the eastern sides of the interior mountain ranges, and that's the one that's shown there in the graphic. And finally, the Santa Ana winds you might have heard of. They're quite common at this time of year, and they occur there just around between Los Angeles, or maybe north of Los Angeles, and San Diego. You can see that high pressure there in the Great Basin, they call it, and that sort of directs winds up over the Sierra Nevada mountains, and therefore they're quite high, and then they literally fall down on the other side of the mountain, heating up at the dry adiabatic lapse rate as they do, and also they follow through the gaps in the mountains. And those winds can be extremely strong, dry, katabatic winds affecting the coast. You can see the other graphic there. You can see the winds. They're northeasterly, blowing all that smoke from wildfires out over the sea. And that's quite common. Of course, they're also known to initiate wildfires because the winds are so hot and dry. So the Santa Ana winds. He even writes songs about the Santa Ana winds. Some of you might recognize the lyrics there from the Steely Dan song. So coming to the end, we'll just take a closer look at a few local wind videos that I did earlier. So I'll still be talking, but it won't be live. You'll be glad to know that they're very short. The first we'll look at is just a description of foehn wind and also foehn cloud. It's self-explanatory. I won't go say anything more about it now, but you'll be glad to know the video only lasts 1 minute 35 seconds. And even better, when we get on to the next one, it's just describes very, very briefly how the Marseille Mistral, I'm sure you've all heard of how that tends to form. And the third one then, again, just a short minute and 8 seconds. I was lucky enough just to see on the charts a levanter blowing in Gibraltar, so I made good use of that. So we can see that shortly. And then just slightly longer, 4 minutes 48, a description of the formation of sea and land breezes. For those aspiring PPLs amongst us, and certainly the foehn wind would form part of the meteorology examination, and also sea and land breezes would feature in the PPL course. The other local winds would be more for CPL, I think. So will we start with the foehn wind? They're little videos, and they were made actually by myself for another project, and we'll see how we get on. Okay. Foehn winds are warm, dry winds that flow down the lee side of a mountain. When winds encounter a mountain which is high enough to block their passage, the air rises along the mountainside, cooling as it rises at the dry adiabatic lapse rate of 1 degree per 100 meters, until it reaches saturation at the lifting condensation level. As the water vapor condenses to cloud, it releases latent heat, and further lifting of the air causes it to cool at the lower saturated adiabatic lapse rate of 0.5 degrees per 100 meters. Precipitation on the windward side causes the air to lose most of its moisture by the time it reaches the mountain top. As the cold, dry air descends on the leeward side of the mountain,
it warms at the dry adiabatic lapse rate throughout the descent to the valley floor below, reaching much warmer temperatures than they were on the other side of the mountain. Foehn winds can be very strong, causing structural damage. The hot, dry Santa Ana winds in California are known to promote wildfires, and in springtime in the Alps, the sudden rise in temperatures linked to foehn winds can lead to rapid melting of snow and avalanches.
That's the foehn wind, and I also picked up from that in southern Bavaria, close to the Alps, for example, they have microclimates there that are much different and warmer than the rest of Germany, or at least northern Bavaria and the rest of Germany, because of the prevalence of these warm foehn winds. So the development of foehn cloud and also foehn winds are tested, I think, quite regularly at the PPL level. So we'll move on to the Mistral. The Mistral occurs when there's an area of high pressure in the Bay of Biscay and an area of low pressure around the Gulf of Genoa. The flow of air between the high and low pressure areas creates a current of cold air from the north, accelerating it through the lower elevations of the Rhone Valley. Before we finish that one, you can see that at Marseille, during this event, the surface wind was 320 degrees, 38 knots, gusting 49 knots. So that's a typical Mistral. So let's move on to the next one now, the Levanter wind. The Levanter wind is an easterly gap wind that frequently blows through the Straits of Gibraltar. The strongest wind occurs when there is high pressure to the east over the Mediterranean and low pressure to the west of Gibraltar. The high pressure conditions lead to atmospheric stability in the low-level airflow, strongly suppressing vertical air motion. The narrow gap, combined with the pressure gradient force, produces strong Levanter winds through the strait. Here you can see the associated METAR for Gibraltar Airport, where the surface wind is 090 degrees 30 knots, gusting 44 knots, in poor visibility and moderate rain. Sometimes the Levanter can form a characteristic banner cloud over the Rock of Gibraltar. However, this is not always the case, and a particular set of conditions is required for its formation. So last but not least, the sea and land breezes. So a little bit longer, but again, it is quite relevant to the PPL. Here we go. A sea breeze is an onshore breeze that develops around large lake shores and coastlines on warm sunny days. In mid-latitudes, sea breezes are common during spring and summer, when there's a large temperature difference between the sea and adjacent land areas. To see how a sea breeze forms, imagine two columns of air, one over the sea and the other over the land. Initially, both columns of air have the same temperature, volume and mass, so the surface pressure over the land and sea is the same. As the sun rises, it radiates heat equally over both land and sea. However, the land heats up much more quickly than the sea, as water has a higher specific heat capacity, requiring a lot more of the sun's energy to heat it up. The land heats the air above it by convection. The warm air expands, becomes less dense, and rises upwards in the column. As air is redistributed upwards, the pressure at higher levels in the warm air column increases. This means that, at the same height, pressure is higher in the air column over land than the air column over the sea. This causes a pressure gradient to form between both air columns. Air at the upper level starts to flow offshore from high to low pressure, converging with the air column over the sea and descending towards the surface, thus increasing the sea level pressure. The pressure gradient force at the surface now causes an onshore flow towards the lower surface pressure over land. This onshore component is what we experience as the sea breeze, and the circulation pattern is complete.
Where the incoming cool air meets the warmer land air, the opposing winds can force the air upwards, where it cools and can condense to form convective clouds and even thunderstorms. This convergent zone is known as a sea breeze front, which behaves like a mini cold front. Pilots can expect wind shear and turbulence in the vicinity of this sea breeze front. Sea breezes can be disrupted or prevented altogether by strong prevailing winds, significant winds flowing parallel to the coast, or temperature decreases over land due to the cooling effects of precipitation. Generally, coasts are sunnier than inland. However, sea breezes can also bring in offshore low clouds, mist and sea fog to spoil a sunny day on the coast. Initially, the sea breeze blows perpendicular to the coastline, but as the wind strength increases, it is acted upon by the Coriolis force, an apparent force resulting from the Earth's rotation, and in the northern hemisphere gradually deflects the onshore flow to the right during the afternoon. The shape of the coastline can greatly influence how separate sea breezes interact with each other. Headlands and peninsulas are particularly susceptible to enhanced convergence of sea breezes, causing the colliding air to give rise to frequent heavy showers and thunderstorms along the convergent zone. A good example of this peninsula effect is the state of Florida, which is called the lightning capital of the United States, having averaged 223 strikes per square mile in 2021. With clear skies at night, the situation reverses as the land cools to below adjacent sea temperatures. In this case, the pressure increases in the upper levels over the sea, and the resultant circulatory airflow is from land to sea at the surface. Land breezes are generally weaker than sea breezes due to lower temperature gradients and contain less moisture. It's about 1 o'clock in the afternoon on the 28th of April 2022, and there's a nice cool easterly breeze coming off the sea on the east coast near Clogherhead in County Louth. The sky is clear out to sea, but when I turn the camera around, you can see some convective cumulus cloud inland, possibly caused by a weak sea breeze front lifting the warmer air over land.